In this video, we'll explore and define the concept of orthogonal projection. Here, I have drawn a purple point and a black line. That black line is a subspace. It's the span of a single vector. Imagine I have a flashlight above the point, and I just shine a light and cast a shadow of that point directly onto the subspace. And I do this so that the shadow lands at a right angle. Where that point lands on the subspace is the projection of the point onto the subspace. Now, the only thing wrong with the flashlight analogy is that typically a flashlight will inflate the size of a shadow, giving you a larger point in the projection. That will, of course, not happen here. I'm only talking about the location of where the shadow would land. Now, let's expand that a little and imagine this data cloud here in 2 dimensions. To really use a flashlight as an analogy, I have to imagine flashlights coming from above and below the points, but again, pointed at a right angle, orthogonally, at the subspace. And each point moves to the closest point on that subspace. That will form the projection of the data, in this case, onto the span of E1, that horizontal elementary vector. We can do the same thing to project the data onto the span of E2, using flashlights that come from the left and right. Again, every point moving to the closest point on the vertical axis. The closest point, of course, again, will always be at a right angle. This is the projection of the data onto the span of E2. Now, we don't usually think about it this way, but when we drop a variable, omitting it from our analysis, this is essentially what is happening. We've projected the data onto the span of the other basis vectors. I'm going to try to give you a little glimpse of application here, combining our knowledge of a change of basis with the idea of an orthogonal projection. Now, any example that I can fit on a slide is totally contrived. Here I have 2 variables, x1 and x2, and a third binary variable that talks about whether each point was a success or a failure. Now, I want you to stretch your imagination and suppose that 2 variables is just too many. We need to reduce the dimensions of this data. Obviously, that's hard to think about, but it's not hard to think about if I told you I had 1,000 variables. So one of the options is to simply drop one of our variables. Let's do that. Let's suppose we drop x2. Well, that would mean the resulting data is one-dimensional in nature, and it only involves the coordinate along x1. Again, that's an orthogonal projection of the data onto x1. Now, you can see if my goal here was to come up with some set of rules to separate the successes from the failures, I'm going to have trouble if I use this one-dimensional representation of the data, because I have a good deal of overlap between points in the middle. Now, the same thing would happen if I drop x1. This animation is going to move a little faster because for some reason I could not get the dots to move at a precise right angle. But the resulting projection is correct. And again, I have this overlap in the middle. So if I were to use only x2, I would have difficulty coming up with a rule to separate the successes from the failures. Now, what if we took a different approach and we decided to change the basis? What if I wanted to draw new axes? And those axes looked like those drawn here. Now, it would be unusual for us to draw a picture in this way with axes on a tilt. We tend to like to have our pictures, you know, perpendicular to the horizon or parallel to the horizon. But now I have some new variables, V1 and V2. So what happens when we drop one? If I drop V2, I find I have this one-dimensional representation where the data is nearly perfectly separable. I could easily come up with a rule, maybe to split when V1 is greater than 0 and less than 0, a rule that separates those successes from the failures. Now, this example helps me illustrate the idea that changing the basis is sometimes useful. However, it can be a little misleading because I drew these axes with that target in mind. And in the future, we likely will not be drawing the axes with the target in mind. Still, I think this example is helpful to help students see the point. In summary, most dimension reduction methods do what we just saw. They draw a new set of axes, create a new set of coordinates for the data along those associated basis vectors. This would be the picture where we rotated those new axes to be parallel to the horizon. And then the data is projected orthogonally onto the preferred axis. We'll get into more detail about what I mean there. But preference is given to the preservation of patterns and information, which is generally summed up in variance. Now, this last point is something we're going to spend a great deal of time talking about. So if it's not clear now, that is okay. Now, a question I have for you is whether or not the predicted values in a regression analysis are orthogonal projections. So here I have some blue data points. There is the regression line. Are the predicted values orthogonal projections? No, because they are not projected orthogonally onto the regression line. Preference is given to the target. We are trying to find the point on this line that minimizes the distance between the y value at this point and the y value at this point. The predicted y and the actual y, the residual. All right, so here is some practice. Just drawing orthogonal projections so that make sure that the concept is clear.